First, we'll construct the frame. I'm using steel tubing left over from a previous project, but there are a lot of other materials that can be used. One side of the frame is built higher than the other, so water will flow through the channels by gravity. The water channels are made from vinyl downspouts cut to a length of 30 inches. Holes are cut every 6 inches on center. Since hole saw bits tend to tear vinyl, run the bit in reverse to get a nice cut. You can also alternate the hole positions every other channel to create a checkerboard pattern that maximizes space for plants to grow. 1-inch PVC was used for pumping water to each channel. Cement a cap to each end and use a T in the center with an adapter that will be used to connect a hose to the water pump. Last, drill 5 holes in the side and insert rubber grommets to seal the microtubes that will be installed later. 4-inch PVC was used for water collection. Cut off a few inches from the end caps to make them narrower, then cement them to the ends of the pipe. This is done to give a longer length opening. Make a straight cut along the length of the pipe from end cap to end cap. Make 2 more cuts along each end, creating a long flap. Use a heat gun to soften the PVC and open the flap enough to allow a channel to fit inside the opening. Then drill a hole for the bulkhead adapter. Apply heat to soften the PVC to allow it to conform to the adapter when it's tightened and make a watertight seal. Install the water collection pipe on the lower end of the stand and the water inlet pipe on the higher end. Alternate the channels across the stand to create a checkerboard pattern with the holes. Next, install the water pump to the inlet pipe and a drainage hose to the water collection pipe. The last step before starting the water flow is to drill a 1/4-inch hole in the inlet side of each channel, then install the microtubes from the grommets to the channels. Now we can fill the reservoir, turn on the pump, and see if everything is watertight. We now have a basic functioning hydroponic system, with adjustments to the water chemistry needing to be manually performed. To automate the system, we'll need a control panel to interface all our sensors and devices. The sensors I'm installing will be able to measure air temperature, humidity, vapor pressure deficit, and carbon dioxide, water temperature, pH, and electrical conductivity, as well as water flow rate, water level, and power consumption. Since this is a prototype system, the connections at the control panel are made on breadboards. However, if this were to be put into a production system, you'll probably want to develop your own circuit boards, solder your connections, and add protection from water. Next, I'll push connections for an LCD through the grow tent wall. This will allow me to install an LCD to display measurements and stats on the outside of the tent for easier viewing. For measuring power, I'm using a split transformer that converts the electrical current being consumed by the system to a voltage. Up to 20 amps can be measured by this transformer, with a maximum output of 1 volt. This voltage is then converted to a digital signal by an analog to digital converter, so we can ultimately determine how much current has been consumed over time. I chose to sacrifice a small 1-foot extension cord to get a single wire to clamp, rather than cutting into my power strip. Now we'll set up the pumping system for the nutrient and pH solutions. I modeled mounts that will hold a bottle below each peristaltic pump in Fusion 360, then printed them using Cura and Octoprint. measuring water level, we'll need to mount a pipe that'll enable us to adjust our float sensor to different heights. Next, we'll build a reservoir for our electrical conductivity, pH, and temperature sensors to measure the water. We want to separate these sensors from the main reservoir to allow any chemicals that are added sufficient time to mix before reaching the sensors. To do this, we'll divert a small amount of water from the main flow to the plants to fill up the reservoir, which will then spill back into the main reservoir. This lid I modeled and 3D printed will hold the probes. We'll need to drill a new hole in our water inlet pipe and use a rubber grommet to seal the microtube. Installing the flow meter is simple if using compression fittings. Just cut the microtube where it looks like a good fit and press the ends into the fittings. A fan was added near the top of the tent to exhaust air and to help control temperature and humidity. Now let's build the box that will allow the Raspberry Pi to control our electrical devices. This will consist of 4 AC wall outlets that are individually controlled by 4 relays, which can be switched on and off by the Raspberry Pi. We can now connect an AC power cord to the box, connect the Ethernet wire to our control panel, then plug in the devices we want to control. I also put everything in a battery box to protect against water. Installing the software is simple. First, flash the Raspbian OS image file to a micro SD card. You can now insert the SD card and power up the system for the first time. Installing Mycodo is even easier. Once logged into a terminal on the Raspberry Pi, execute the install command provided on GitHub. Let me give you a brief showcase of Mycodo before I demonstrate it working. For the sake of time, I've already configured everything, but this is all detailed in the accompanying write-up. Once you log in, you're greeted with the latest measurements from our sensors and devices. For a more detailed view, we can create custom dashboards with a number of different widgets available to display data and allow us to interact with the system. This dashboard displays information about water measurements, air measurements, flow and electrical current consumption, as well as a live stream with the Raspberry Pi camera. Each of our inputs are configured on the data page, where you can configure options such as measurement period, which measurements to record, among others. On the outputs page, we can configure our 4 peristaltic pumps and 4 relays. We can also test our outputs to ensure they're working before using them in the rest of the system with our automation tasks. Calibration is a crucial task but can be tedious. Mycodo makes this easy by providing walkthroughs for the calibration procedures for several devices, including the peristaltic pumps and pH and electrical conductivity sensors we're using here. Once we have inputs and outputs configured and working properly, we can combine them to perform autonomous tasks. The most simple of these are simple timers, which we're using to turn our lights on from 3 AM to 8 PM. Next, we have our most complex function, which monitors and regulates the water pH and electrical conductivity. This type of function is called a conditional controller and allows different conditions and actions to be used within Python code created by the user. Here we have two measurements, our pH and electrical conductivity, with several actions for manipulating the peristaltic pumps. We essentially have minimum and maximum allowed values for each measurement. If our measurements fall outside these ranges, the peristaltic pumps will dispense small amounts of solution to bring them back. This function will run every 5 minutes, giving the sensors enough time to adequately detect the change in water chemistry before checking the measurements again. The next function is a PID controller that adjusts the vapor pressure deficit to an optimum range with a humidifier and exhaust fan. There are also simple monitor functions that will send an email to me if certain measurements aren't what they should be. I also have a function to trigger the remote shutter of my DSLR camera every 3 hours to create a high-quality time-lapse. And last, there's a simple timer for ensuring the exhaust fans run periodically to bring in fresh air. We could also create more functions, such as incorporating the CO2 sensor for regulating exhaust, but this is a good set to start with. Let's go ahead and activate our pH and EC regulation function and see it in action. Since the addition of nutrients will impact pH, the function will first add nutrients until the water's electrical conductivity rises above 800 microsiemens per centimeter. Then either acid or base will be added until the pH returns between 5.5 and 6.5. I cultured a biocontrol agent to protect from microbial pathogens and contaminants. This is a bacterium named Streptomyces griseoviridis, commercially known as Mycostop, and will colonize the whole system, including the plant roots, preventing many harmful microorganisms from establishing. Now that we have the proper water chemistry and light schedule, we can plant our seeds. The seeds I'm planting are basil, along with red and green oak leaf and butter lettuce.